right, this is section 11.8. We are going to spend 2 days on binomial distributions. Today we're going to focus just on finding the binomial probabilities and what that means. And then tomorrow we'll look at expanding it and looking at the whole binomial distribution. All right, and this is our last section before we start. We'll take a quiz on Friday and then review for finals. Okay. All right, so the first thing it says we can use binomial probabilities in situations that involve two possible outcomes. And typically we define those outcomes as success and failure. Okay, what is it that we want to have happen? That's called our success. What is it that we don't want to have happen? That's our failure. Okay, so it either happens or it doesn't. So two possible outcomes. So a binomial experiment has these important features. There are a fixed number of trials. Okay, so they're going to tell you how many trials the experiment ran. Each trial has two possible outcomes. Again, what we call success versus what we call failure. Okay. The trials are independent, meaning what happens in the first trial has no effect on what happens in the next trial. And the probability of each outcome is constant throughout. So if I say there's a probability of success of 40%, that means the probability of success on every trial is 40%. Okay, it stays constant. All right. So when we talk about binomial probabilities, we define n to be the number of trials. Okay. It says, suppose you have n repeated independent trials. Each has a probability of success p. Okay, so the probability of success is p. The probability of failure, they use the letter Q for that. And the one thing to keep in mind is only two things can happen, right? So if there's a 40% chance that it happens, what's the percent chance that it doesn't? So the percents have to add up to 100 or the decimals have to add up to 1. Okay? So that's what this part was saying. All right, so if we have that as our definition, it says the binomial probability of X successes. Okay, so X is defined as the number of successes. Okay, and our formula says P of X. Okay, so let's say the probability of 5 successes equals NCX. So the number of trials is your first number here. The number of successes is the second. Okay, so if I run 10 trials and I want 3 successes, I would say 10C3. Okay, then we have P to the X power. P again is the probability of success, and we wanted X of those. And then Q is your probability of failure, and we have the remainder of those. Okay? Yesterday, we did something very, very similar to this. When we took each row of that binomial expansion, right? The very first number that we wrote down came from Pascal's triangle. Well, NCX, those are all the numbers in Pascal's triangle. So you can do this a lot like what we did yesterday. Okay? So we can use Pascal's triangle to get those NCXs. All right. Okay, so our first example. It says, as part of a promotion, a store is giving away scratch-off cards. Each card has a 40% chance of getting you a prize. Suppose you have 5 cards. Find the probability that exactly 4 of the 5 cards is going to reveal a prize. So our 2 outcomes is you get a prize or you don't. Does that make sense? So they're asking for us to figure out the probability that we get 4 cards that have prizes on them. So our number of successes would be 4, right? We want 4 cards to give us a prize. Okay, how many cards do we have total? So that would be the number of trials. Okay, so N is 5 because we have 5 cards. Okay, those are like our trials. Okay, X is going to be 4. We want 4 prizes. Okay, what is the probability that a card gets you a prize? They said 40%. So that is P in our formula. Okay, 40% or 0.4. So if P is 0.4, what would Q have to be? So the probability of failure would be 0.6. Yes? Okay. And if we have 4 successes, how many failures? How many trials did we have? We had 5 cards, right? If we want 4 of them to have prizes, then the other one would not have a prize. Yes? So setting up our formula, we said NCX, P to the X, Q to the N minus X. That was the formula on the previous slide. N is the number of trials. So we have 5 trials. X is the number of successes, and we wanted 4 of those. Okay, so 5C4. The probability of success, okay, and my board was being kind of wonky earlier today, so we'll see if this works out. Probability of success was 40%, and we want how many of those? We need 4 of those. So that's like saying 40% times 40% times 40% times 40%. Okay, we need 4 of those things. And then we need 1 failure. Okay, and that was 0.6. So go ahead and grab your calculator. And find 5C4. All right, so 5C4, you calculated that. You said that was a 5? Yes? So use your calculators now. Take 5 times 0.4 to the 4th power and times 0.6. You should be able to multiply that all in one string. .0768, so about 8%. Yes? So we have about an 8% chance that 4 of those 5 cards are going to get me a prize. Okay? All right. Look at the second part of this. It says, what is the probability that the number of cards that reveal a prize is 0, 1, 2, 3, and 5? In other words, they're looking for us to figure out all the different possibilities. We already figured out 4, right? We figured out P of 4. Yes? So we are going to set this up, and actually once you type it in your calculator, it's easy to adjust for the next row. So the probability of no successes. Okay? The probability of 1 success. The probability of 2 successes. The probability of 3 successes. We already did 4, and now they want 5. Okay? So going through our formula, we need NCX, right? So how many cards were there? 5. In this first one, we want no successes. Okay? So the probability of success was 0.4, and I want none of those. And then the probability of success was 0.6, and I need how many of those? I need 5 of those, right? I want all 5 cards to be failures, basically. No successes. The 0.6 is the failure. I need 5 of those. Okay, we're good. All right, so the probability that one card is a success, that gets me a prize, would be 5C. How many successes do we want? 5C1, and then 0.4 to the first power. I want 1 success. And how many failures do I need? 4. Yes? Okay. If I want 2 successes, now it's going to be 5C2, and then 0.4 to the, how many successes do I want? 2, and 0.6 to the third. Yes? 2 successes, 3 failures. All right, so what's the next one going to be? 5C. Five C what? Okay, it's not just Bo giving me an answer, right? Everybody, 5C3, then what? 0.4 to the? All right. I'm sure that picked up in the recording. Thank you. All right. Last one. 5C5. 0.4 to the fifth and 0.6 to the 0. Okay. So if you type this in your calculator, type 1 row in, it's easy to recall it and change your powers. Yes? So I'm going to pause it. I want you to give me a decimal for each of these. All right, let's look at what is the probability of no successes? What decimal did you come up with?
0.07776.
Okay, somebody else. 1 success.
I got 25.9%.
So 0.2592. Okay. Third one? 0.3456. Fourth one, yeah. Next one, fourth one. 0.2304. And last one? 0.0102. Okay, 4. Okay. Now, we had already calculated the probability of 4 successes up here, right? If we took all of these numbers, this one, and all of these, and added them up, what would we get? We'd get 1, right? 100%. Because we've accounted for all the different things that can happen, anywhere from no successes all the way up to all 5 being successes. Yes? We'll deal more with that tomorrow. That's called that binomial distribution. How are we distributing all the different percents? Okay? What did you say? The best chance? All right. Now, this, I'm going to have you alter a little bit to make it match more what we're doing. Do you remember in Pascal's triangle that every row was symmetric? If you read it from the left, it matched the same as if you read the row from the right side? Okay. All of these NCXs really come from Pascal's triangle. Okay, so I'm going to have you alter this a little bit so that it kind of fits with what we're talking about. So instead of NC0, we're going to say NCN for that first one. Our next one's going to be NCN minus 1. Our next one is going to be NCN minus 2. Okay, so instead of these, we're going to use these other versions. Okay, and it's going to go all the way down until we get to NC0. Yep, the A's and B's are the same. Okay, so in this case, A is like our p-value in the last example, right? The probability of success, and B is like the probability of failure. Your row of Pascal's triangle worked the same front and back. In other words, NC0 and NCN really were the same number. Okay, so that's why we were allowed to reverse that, and it's just going to match more of what you're used to doing. All right, so our next example. Our calculator allows us to do these combinations, right? So someone asked yesterday, do we have to memorize Pascal's triangle? Well, not really, because you can calculate them all with NCRs or NCXs. Okay. Is it faster if you have Pascal's triangle ready instead of typing in NCX a whole bunch of times? Sure. So I'm okay with you using either version, but I want you to know that both are out there, both work. Okay. So if we were going to expand this like we did yesterday, we would have looked up Pascal's triangle and our first numbers would have been what? 1. No. The numbers, there are coefficients for this. If we're expanding it to a 5th power, we would start a row with 1, then 5, right? So flip back in your to Pascal's triangle notes from yesterday. Our numbers were 1, 5, then what? 10, 10, 5, 1? Yes? Okay. Those are the same thing you would get if you did these combinations, NCX. Okay? So this would be NCN. In this case, N is 5, right? We're expanding it to the 5th power. So we'll write this as 5C5. This is going to be 5C4, 5C3, and just check. Type in your calculator, 5C3. Do you get a 10? Type it in. 5C3. Do you guys remember the combination formula? NCR was n factorial over r factorial and n minus r factorial. Yes? So if we were doing 5C3, we would start out with 5 factorial over a 3 factorial and a 2 factorial. Yes?
For permutations, if it's like 5C4.
Are you talking about permutation? So 5P4?
Yeah, 5P4. So then you just do like 5 times 4, right? Or something like that. Or is 4 how many multiply? Or is
Okay. It'll be the same thing here. We just don't have this extra 2 factorial in the bottom. So 5 factorial is 5 times 4 times 3 times 2 times 1. Yes?
Yeah.
3 factorial is 3 times 2 times 1. Okay, so these are all gone. 2 factorial is 2 times 1. I can reduce 4 and 2 to 2 and 1. 5 times 2 is 10. Yes? Now, I asked you to just type it in your calculator, 5C3, and get 10. Yes? You guys didn't want to do that, so we'll do it the long way. it works, yes? No? All right. So the idea here is if you are looking at binomial experiments and finding binomial probabilities, you can use the NCX feature, or you can look it up in Pascal's triangle. Okay? All right, so expanding this, what did we do with X? What was its first power? The first one starts out high, right? So we had X to the fifth, and then it went down, right? Which is the same thing that our probability of success was doing, right? This number was matching this number. Okay, our power here is matching our power here, our X or R value, whichever way you're looking at it. Then we had to expand the Y piece, and Y started with our smallest number and went up, yes? Okay, so my whole answer was what? Give me the whole polynomial, all these pieces strung together. X to the fifth plus hang on. Our next term was 5x to the fourth, y to the first. Yes? Okay. Our next term is 10x to the third, y to the second. Yes? Okay. Then we had 10x to the second, y to the third. Then we have 5xy to the fourth. And our last one, y to the fifth. Okay? So what I want you to see is that each of these pieces, okay, each of these terms is really the same thing we just did over here, right? Each of these terms. Here's one, here's one, here's one, here's one. Okay? So we're really setting it up the same way that we did when we were expanding a binomial to figure out binomial probabilities. All right. We did one like that yesterday. Oh, no, we didn't. This one is just asking us for the third term. That means they don't want us to come up with the whole big polynomial. They just want us to find the third number. Okay? All right. So our third term, let's start, how would we start expanding it? We would have said it's fourth row of Pascal's triangle, right? So what's my numbers in Pascal's triangle when it starts with a 1, then a 4, then what's the next? 6? Okay, so my first would be a 1, then a 4, then a 6, right? And it would keep going. But I only want the third term. So I only need this piece, right? But it sometimes helps to start the pattern. So it would have said, now I have to take my 2x, right? And 2x starts out with my highest power, which would be a 4. And then it goes down. Okay. Then we take our second term, which is a negative 3y, and it starts with the lowest power and goes up. Okay? So all they want me to do is to calculate this one. They want my third term. All right, so we have 6 times what? 2x, if I square it, becomes 4x squared. What's negative 3y squared?
9y squared.
Okay, So in terms of my variables, I'm going to have an x squared, y squared. Okay. What do I get for my front numbers? What's 6 times 4 times 9? Okay. So this would be the third term of my whole big polynomial. Okay. All right, questions on that? Okay, I'm going to have you guys do the got it one. When you're finished, let me know and I will check it, and then we'll move on to homework. All right, take a second, check your answer. Make sure you catch me during work time if you are not getting this correct. All right, I want to make sure we know how to expand binomials. I am going to add one question. Go ahead and put this in the summary section. There should be room or underneath the summary section. All right, we are given we are expanding binomial x minus 2y. We're expanding it to the 8th power. I want you to find the 6th term. That doesn't mean you have to find all 6, right? You find the 6th one. But my recommendation is that you start the pattern, okay, so that you can figure out what your powers should be. So what row in Pascal's triangle would we need? It starts 1 and then 8? Okay, so 1, then 8. Okay, so first, second, third, fourth, fifth, sixth. We're looking for that one, right? Okay, so we've got our NCX piece figured out. Now, we need our probability of success, or our first term, which is an x, and it's starting out to what power? It's starting out to the 8th. So then this would be to the 7th, 6th, 5th, 4th, 3rd. Okay, then what? So do we have to fill in all of the negative 2y's, or can we figure out what the powers should be?
You can figure it out because it's just 6. Or, yeah, no. 3, 2, 3. Wow, 3.
Let's make a decision here instead of just tossing out numbers. This would be to the 0, 1st, 2nd, 3rd, 4th, 5th. Now, think about it. Your powers have to add up to what? 8. So if we already calculated that this is going to be to the 3rd power, we know this is going to have to be to the 5th power if they have to add up to a power of 8. Yes? All right, so go ahead and calculate. Negative 2 to the 5th is what? Okay. So we have 56 times x cubed times negative 32y to the 5th. What's 56 times negative 32? Let's not guess. Let's actually type it in. Okay. And then our variable parts would be x to the 3rd, y to the 5th. Yes? All right. Come on. It's not letting me go there. Okay. So take a second and write a summary of what we've done so far. All right, once your summary is done, you guys are going to be doing day 1 for homework.